Hello everyone and welcome back to the second part of the grade 10 revision for end of term 3, and we'll talk now more about kind of the introduction to quantum physics or quantum mechanics when it comes to the Young double slit experiment and investigation, and basically continuing with light and constructive destructive interference and so on and so on and so on. It's quite easy. But my style, honestly, when it comes to revising, is revising the only equations. So we'll only revise the equations and how to use them to solve. And for the other topics, when it comes to describing the phenomena more and all of that stuff, when it comes to the reading part, where you have to kind of read and understand from your reading and go into the book, I will not explain that much because I studied it at some point, but a lot of the information might be a little bit rusty. However, when it comes to equations, I'm of course great at them. I love equations. So let's talk about the first equation. Now, when it comes to Young's double slit experiment or investigation, so what he did is he made these quite small, basically slits, and he made light pass through them, and he saw this phenomena where the light goes in some sort of bands, and this kind of indicates that light is waves, but it could be also particles at the same time. Here we had this kind of debate between Newton and other scientists that believed that light was waves, not particles. But again, in reality, we have the two kind of ideas, the two formalizations, and in this case, we will deal with them as waves, and we can calculate lambda to be x d divided by L, where L is the distance between the slits and the board or the thing you're shining the light at, and then D is the distance between the slits, and X is the distance between two consecutive bands, so either from red to red or from black to black. So this is the equation that we are going to use to solve some questions. So we have this question. It says a double slit investigation is performed to measure the wavelength of red light. The slits are this much apart, so 0.0190 millimeters apart. The screen is placed at 0.6 meters away, and the first order bright band is 21.1 millimeters from the central bright band. What is the wavelength of the red light? So again, we will use this equation. Okay, this is too big. Okay, so we'll use this equation, xd divided by L, and what do we know? So in order to solve this question, let's write the knowns. So x, which represents the distance between each consecutive band, it's 21.1 millimeters, so 21.1 times 10 to the power of negative 3 meters. And then we have d, which is 0.0190, this is the distance between the slits, times 10 to the power of negative 3 again, millimeters. And then L is 0.6 meters. So let's substitute. So this goes here. So lambda is going to be 21.1 times 10 to the power of negative 3 multiplied by D, 0.0190 times 10 to the power of negative 3 divided by L, which is 0.6. So it's going to be quite a normal number. It's not going to be too big or small. So 21.1 times 10 to the power of negative 3 times 0.019t negative 3 here, and then that's divided by 0.6. The answer is a very, very small number actually, yeah. So 6.68 times 10 to the power of negative 7. So this is the wavelength in meters. This is our answer. Now for this question, it's extremely similar, so let's write the question again, or the equation, sorry. So lambda is equal to xd divided by L, and this time, what do we know? We know the wavelength of the light, so lambda is known. So lambda is equal to 542 nanometers, which is equal to times 10 to the power of -9, okay? And for, let's see, what do we have? We have the distance between each kind of band, so it's 4 centimeters. So we know d, not d, but x. So we know x is equal to 0.04 meters, and we know d, or we know L, to be equal to 1.2 meters, and the thing that we don't know is d. So let's substitute these numbers into the equation that we have. So 542, but maybe let's use another color. So 542 times 10 to the power of -9 is equal to x, which is 0.04, times d, which is the thing that we don't know, divided by L, which is 1.2. And we can solve for d is equal to 2 times 542 times 10 to the power of -9. So not 2, but 1.2. So 1.2 divided by 0.04. Let's find it. I only do that to make calculations quicker. So 1.2 times 542 to this power divided by 0.04, and the answer is 1.625 times 10 to the power of -5 meters. Or we can say that if we move this to here, so we can say it's 0.01625 millimeters. So this is our answer. Now here we have the thin film interference problem, or the equations for it. So we have for constructive and destructive interference, and the reason why I attached here the picture of the iPhone X or the iPhone 10 wallpaper is because many people think it's a made-up planet, but in reality this is a soap bubble, and with the right lighting you can see kind of how brilliant and amazing looking thin film interference is. So you can see how there are different colors that are being displayed because of basically the waves refracting in different angles. Therefore you can see the different colors of it, right? And this is interference. Because you have interference, that's why you can see different colors. So again, this is not at all a planet, but it's a soap. And a lot of the times when you wash your hands, for example, and see some bubbles, you will see different colors, and the reason behind that is interference patterns. So we will talk more about that. To solve this question, we will have to know whether the ray undergoes phase shift or not. When does phase shift happen? It happens when you go from a lower refractive index into a higher one. So from 1 to 1.45, yes, we have a phase shift, and from 1.45 to 1.33, we have no phase shift. So we have only one phase shift. This is important because based on that, we can actually conclude the equation that we are going to use. Now it is stated in the question that you observe a colored rings, or basically colored rings, which means you see a bright region. You will not see a bright region if it was destructive interference, rather you will see it when you have constructive interference. So based on that, we know one phase shift, so one phase shift, and we know it's constructive. Based on that, we can choose our equation, and the most suitable equation is 2d is equal to m plus 1 over 2 times lambda film. Now let's see how we can substitute the numbers. So we know that you can see a green kind of region with a lambda of 555 newton meters. So we know lambda of the film in here is 555 times 10 to the power of negative 9 meters. Okay, and what do we know as well? We know that in order to find the smallest kind of d, we will have to use m is equal to 0. This is for the minimum basically. So 2d is equal to 0 plus 1 over 2 times 555 times 10 to the power of negative 9. And let's solve for d. So d is equal to 1 over 2 times 555 times 10 to the power of negative 9, all divided by 2. So d is equal to, according to the calculator, to this much. Let's see. .38. So 1 point, let's approximate it to 1.4 times 10 to the power of negative 7 meters. So this is how small the oil slick is. Okay, so this is how you calculate it. First of all, you identify how many phase shifts. Once we identified it, we want to know if it was constructive or destructive. Once we understood it from the question, then we get to choose the suitable equation. So in this question, how many inversions do we have? So first of all, you will have the first inversion from the refractive index 1 to 1.33, so there is inversion here. And then you have from 1.33 to 1.52, another inversion is here because you go to higher refractive index. So we know that the number of inversions is 2. So let's understand this. So we talked about this equation in the double slit experiment, which states that lambda is equal to xd divided by L. But in this case, when we have a single slit, a single huge slit, here we'll not use this equation, rather we'll use another equation, which is 2x1, which is the distance between the central bright band and the first dark band, is equal to 2 times, what was it, times lambda times L divided by W, or yeah, let me keep it like this. So W, where W is the width of this slit basically. So this is the equation that we are going to use. Sorry, I had to stutter a little bit because I did not study this equation in a very long time. I remember it from grade 10. But again, this is the equation that we're going to use, and let's solve some questions regarding it. So to solve this question, let me remind you of the equation. So 2x1 is equal to 2 lambda L divided by W. And let's see here. So monochromatic green light with a wavelength of 546 nanometers. So we know that lambda is equal to 546 times 10 to the power of negative 9 meters. And it falls on a single slit with a width of 0.095 millimeters. So we know that this is the width, and it's equal to 0.095 times 10 to the power of negative 3. And it is located 75 centimeters from the screen. So L is 0.75 meters. And how wide will the central bright band be? So what we want to solve for is x1. So we want to solve for x1. Let's substitute the numbers. So 2x1, which we don't know, is equal to 2 times lambda times L divided by W. And let's solve for x1, of course neglecting this 2, cancelling it from both sides, and we will get some value. Let's do it. So the answer is 4.3 times 10 to the power of negative 3 meters, which is equal to 4.3 millimeters. Now let's move to the idea of diffraction gratings, and it's quite an easy idea. You just have this equation, so m lambda is equal to d sine theta, and basically m is the order, and most of the time is going to be 1, to be honest, but here you have a third order bright band, so we'll have 3 here. So 3 times lambda. What is lambda in the question? So it tells you here that we have the wavelength 580, so lambda is equal to 580 times 10 to the power of negative 9, and then we will have the separation, which is d, and d is equal to 1900 times 10 to the power of negative 9, all of them of course in meters, so this is 9 here. Okay, so let's substitute the numbers, and of course I brought 3 from here, so third order bright band. So 3 times lambda, which is 580 times 10 in the power of negative 9, is equal to d, which is 190 or 1900 times 10 to the power of negative 9 times sine theta, and what we have to do is find theta. That's it. How do we find theta? We just take the sine inverse of both sides, right? So sine inverse of 3 times 580 times 10 to the power of negative 9 divided by 1900 times 10 to the power of negative 9. Now of course you can directly put this in the calculator, however I rearranged it because I love algebra and I think the calculator works faster like that. So sine inverse of 3 times 580 times 10 to the power of negative 9 divided by the value down there. So let's see. We'll get approximately 66.3 degrees, and this is it. So this is the equation that you are going to use, and using it you just solve the questions. It's that easy. So let's move to the idea of velocities, and it's just vectors, right? It's just playing around with the vectors, and if you want to know more in-depth information about vectors, then I recommend that you go to my end of term revision for grade 11, the first part, and in there I discuss vectors but in too much details, but here I think I will talk about it simply. So if we have, for example, a vector that is going this way, so for example this is the velocity of a car, for example, and we have maybe some wind that is going in this direction, or not this direction but something like this, so this is v wind, for example. So what is the resultant velocity of the car itself? Well, a car is not a very good example. Let's say a plane, for example, because cars do not usually move much when there is wind. So to find the resultant, we will have to bring them to each other like this, where this is the velocity of the wind and this is velocity of the plane. So I bring them close to each other, and the resultant velocity is going to be this. So this is the velocity of the plane with the wind. Okay, and to solve it, so to find VPW, the answer is going to be the square root of VP squared plus VW squared. And to find this angle here, let's call it theta. Theta is going to be equal to tan inverse of the VW divided by VP. So we will take more examples, of course, but this is kind of an intro to this information. So let's solve this question. It says a motorboat heads due west in 30 meters per second relative to a river that flows due north with 5 meters per second. What is the velocity with both magnitude and direction of the motorboat relative to the shore? So let's try to draw it. So we have a river that flows due north in 5 meters per second, and you have a motorboat, which is quick, so it goes in 5 or not 5 but 13 meters per second. So what is the resultant velocity? This is a question. What is the resultant velocity of the boat and the shore? And not the shore, but the river. Because the resultant velocity is going to be the velocity relative to the shore. Okay, so let's do it. And the first step I will do is just move this vector all the way to the other side. So it will be something like this. So, okay, and this is 5 meters per second. And the resultant velocity is going to be this. Okay, and the direction is going to be this angle here, theta. Okay, so let's do it. So to find this velocity, let's call it velocity of the boat and so the boat and the river. So boat, river. So velocity of boat, river is equal to 13 squared under the square root plus 5 squared, and it's equal to some value. Let's find it. So 13, almost 14 meters per second. So this is the resultant velocity. And let's find the direction. The direction, as we know it from here, this is theta, and theta is going to be equal to the inverse tan of 5 divided by 13. 5 divided by 13. If you're not sure why I did that, it's basically because tan is the opposite over adjacent. And what is the opposite? This is the opposite. And what is the adjacent? This is adjacent. So tan inverse of 5 divided by 13 is 21. So 21 degrees. That's a really bad looking too. So this is 21.03 degrees. Okay, relative to the shore. So for this final question, let's just discuss it briefly. It's quite an interesting question, to be honest, because you can see there are a lot of vectors, and it might look complicated, but it's really not. It's all about using projections of vectors, basically the x and y projection. So what I plan to do, I'm not sure how the textbooks do it, but the way I'm going to solve it is like this. So I want to find the projection of this blue line here. I will find its projection. It's this part, right? So I will do this. So the projection of the blue line on the x-axis. And why this is possible is because we have its magnitude and we have its kind of angle direction. So we know that VO with relation to M, x is equal to 5 sine 20, which is equal to, let's find it here. So 5 sine 20, or not sine, sorry, but cosine, because it's the x. So let's change it here. So cosine 20, and it's equal to 4.7 meters per second. Okay, so this is the first important value that we have. Then what I want to do is find the x projection of this kind of vector, because if I project it here as well, so this is a purple vector, let me change its color, maybe use green. So I want to find this part here, this part. Okay, so this part, how do we find it? So it's Vm, so Vm with relation to G, x is going to be equal to 1 times cosine 70. And this is equal to, let's see, so cosine 70 is 0.34, so 0.34 meters per second. Second value, we got it. And now what we want to do using this is to find the y values. But before that, let me explain why I did it. Because using this, I can take the projection of this vector, the green vector here, and write it here. So it's going to be the same as this, right? So in this case, this total thing, this blue and this green, is VO with relation to G, x. And then to find the y projection of VO with relation to G, so to find this part, we will do the same thing, but instead of cosine, we'll use sine. This is the only difference. So to find VO, G, y, we will use cosine. The cosine of the blue vector and the purple vector. So let's do it. So for the blue vector, we will have VOM y is equal to 5 sine 20 this time, which is equal to, let's see, 1.7 meters per second. And for the purple vector, so V m relation to G, Vm relation to G, y is equal to 1 sine 70. And what is it? So 1 sine 70 is 0.94 meters per second. So we got this, and then we got this as well. Using these values, we can find the huge theta here. So theta, let's just give it a quick kind of definition here. What is theta? Theta is equal to the inverse tan of VO with relation to GY divided by VO, not VO, yeah, VO with relation to GX. And this is equal to the inverse tan of, what is VO with relation to GY? Is going to be this plus this. So 1.7 plus 0.94 divided by, what is the other value? So what is VO with relation to GX? It's going to be this value plus this value. So 4.7 plus, so 4.7 plus 0.34. Okay, let me close it to the same color. And the answer is going to be some very nice value. Let's find it. So 1.7 plus 0.94 divided by 4.7 plus 0.34. So 27.6. 27.6 degrees, which is approximately 27.7. So this is our answer. And this is how we solved this question. It's a lot of geometry. So we have 1, 2, 3 triangles that we had to kind of manipulate to solve this question, but it's quite fun, it's quite easy once you take it apart. Once you take it apart, it's quite easy. And this is kind of the end of this revision. I hope it was beneficial for you, and if you have any questions, again, feel free to contact at any time. Thank you.